Welcome to solverfy.
So for part A, if the image is real, then the focal length is going to be positive, and the image distance is going to be positive. Therefore, the magnification is negative. So the distance to the image here, since we're told the magnification is 2.5, the distance to the image is going to be 2.5 times the distance to the object. So using our equation, 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. We find that this is 1 over the distance to the object plus 1 over 2.5 times the distance to the object. We're just replacing that distance to the image with this magnification term is equal to 1 over the focal length, which we know. Therefore, solving this expression for the distance to the object, we find that the distance to the object is equal to 3.5 divided by 2.5 multiplied by the focal length. So carrying out this expression, we find that this is equal to 70 millimeters. And we can box that in as our solution for part A. Okay, well, in part B, so now if the image is magnified, then the lens must have a positive focal length. And because negative lenses always form reduced images, and since the image is virtual, the magnification is positive. Thus, the distance to the image is going to be negative 2.5 times the distance to the object. So therefore, we can go ahead and start a new page here. For part B, we're going to have the same expression. It's going to be 1 over the distance to the object plus 1 over the distance to the image. But now this is 1 over negative 2.5 times the distance to the object. And this, of course, is still equal to 1 over the focal length. So solving this expression for D0, we find that the distance to the object, let's rewrite that to make it look a little nicer. There we go, is equal to 1.5 divided by 2.5 multiplied by the focal length. So carrying out this expression using the same value for the focal length, we find that this is equal to 30 millimeters. And we can box that in as our solution for part B.